Sometimes the biggest secrets in the cosmos aren't hiding in some giant galaxy, but in a single, tiny, distant star. Today, we're going to zero in on one of those, Pulsar B1641-45. This thing has been a cosmic amplifier, a super precise probe, and a mathematical puzzle all rolled into one. So yeah, let's get into it.
Here's the plan. First, we'll get to know what this pulsar actually is. Then, we'll see how it led scientists to a huge discovery, what it taught us by showing them, well, nothing at all, and finally, how it revealed this hidden order inside its own chaotic signals. By the end, you're going to see why this one star is such a big deal.
All right, let's meet the star of our show, Pulsar B1641-45. Its story starts thousands of light years from here, and every single pulse of light we see from it has made an epic journey across empty space just to reach our telescopes.
So, what even is a pulsar? Okay, imagine a star, way, way bigger than our sun. It runs out of fuel and boom, it collapses in on itself. What's left behind is this city-sized, incredibly dense core called a neutron star. Now, if that core is spinning really fast and shooting out beams of radiation, we see it as a pulsar, flashing on and off like some kind of cosmic lighthouse. And this particular lighthouse? Wow, it is seriously far away. We're talking 15,000 light years, over in the constellation Norma. To give you some perspective, the light we see from it today actually started its trip around the same time humans were first making their way into the Americas. I mean, just think about that. And that insane distance is exactly what makes our first discovery so amazing. The light from this pulsar had to punch through a lot of interstellar junk to get here, and as it passed through one very special cloud, it let astronomers see something that had never, ever been seen before.
Now, you'd think, right, that a big cloud of gas would probably block some of the light, or at least dim it down. But when astronomers pointed their telescopes at this pulsar as its beam sliced through a giant cloud of hydroxyl gas, they saw the complete opposite.
Instead of getting weaker, the signal actually got stronger. So here's how it works. The pulsar's photons zapped the molecules in that hydroxyl cloud and excited them. But instead of just spitting out random light, the cloud released perfect, identical copies of the pulsar's photons, all heading in the exact same direction. The cloud basically turned into a natural, cosmic laser amplifier.
And this wasn't some tiny effect. Think of it like a photon copy machine. For every 100 photons from the pulsar that went into the cloud, about 105 came out the other side. That cloud was literally making extra light.
So how did they prove this was actually happening? It was such a clever, simple idea. First, they measured the radio signal from that spot in the sky when the pulsar's beam was pointed away from us. That's the pulsar off signal. Then they measured it when the pulsar was flashing right at us, the pulsar on signal. When they subtracted one from the other, there it was, a clear excess signal. The only explanation was that the cloud was amplifying the pulsar's light.
I mean, this was a massive moment in astronomy. The theory had been around for decades, but this was the first time anyone had actually seen it happen in deep space. B1641-45 and that cloud gave them the proof they needed.
But the whole cosmic amplifier thing wasn't the only trick this pulsar had up its sleeve. Next up, we're going to see how it taught scientists something huge by showing them, well, nothing. This next discovery is all about the importance of what wasn't there.
In science, a non-result can be just as groundbreaking as some big dramatic finding. See, a pulsar signal is like this super thin probe that slices through the space between stars. Scientists were watching this probe for years, and they were expecting to see it wobble and change as it moved through clumpy gas clouds.
And here's where it got weird. For most pulsars, the signal is all over the place, changing all the time as it hits these dense, messy patches of gas. But for B1641-45, astronomers watched it for 2.5 years and saw nothing. No change. Its path was incredibly stable, which suggested that the gas it was flying through was shockingly smooth and uniform. To put a number on it, the upper limit for any change in the gas density was less than 10 to the 19th atoms per square centimeter. Now, on a cosmic scale, that is an unbelievably tiny fluctuation. It proved that for thousands of years, this pulsar's light has been on this strangely quiet and stable ride.
Okay, so this pulsar helped us figure out the space between the stars, but what about the star itself? Well, it turns out B1641-45 had one more big secret to give up, and this one was hidden in its own seemingly random signal.
If you look at a pulsar's flashes one by one, they just look like pure chaos.
Some are super bright, some are dim. Their shapes are all over the place from one pulse to the next. It just seems totally random.
So this chaos brings up a really big question. Is it actually random? Or is there some kind of hidden pattern, a secret blueprint that's deciding how every single one of these pulses is built?
For B1641-45, the answer is a huge yes. It turns out that every single chaotic-looking pulse is actually built from the exact same 4 simple mathematical building blocks. They're called Gaussians. Just think of them as simple bell-shaped curves. The only thing that ever changes from pulse to pulse is just how strong or how high each of those 4 components is.
But here's the final piece of the puzzle. Even the way the strength of those components changes isn't random either. It follows a predictable statistical pattern. So the chaos we see is really just an illusion. Underneath it all, there's a simple mathematical blueprint at work, which points to some fundamental physics happening deep inside the pulsars itself.
All right, let's pull all these pieces together. We've seen this one pulsar act as a beacon, a probe, and a kind of Rosetta Stone for its own signals. So, what's the big takeaway here? This one star gave us 3 completely different, really profound insights. It handed us the first direct proof of cosmic amplifiers, its super stable path made us rethink how clumpy interstellar space is, and its pulse blueprint showed us this beautiful, hidden mathematical order inside of what looks like total chaos.
So you see, B1641-45 isn't just another flashing dot in the sky. For scientists, it has become this incredibly versatile tool. It's a probe, it's an amplifier, and it's a key, all at once, unlocking secrets about the universe on the biggest and smallest scales.
And that really just leaves us with this final amazing thought. The story of this one pulsar is such a powerful reminder that the universe is just full of information, waiting for us to figure it out. If a single beam of light after traveling for 15,000 years can teach us all of this, just imagine what other incredible secrets the stars are still waiting to tell us.